G'day. Adam here from Esau Hunting Systems. Welcome to my shed. This is where I make some of the products that we sell at Esau. I hope everybody's keeping themselves occupied while they wait for the rut, wait for the winter months to come back again so we can all get out there and enjoy what we love doing, which is hunting. Some people I know get out there and do it in the summertime, but yeah, that hot weather really does make it less enjoyable. Flies and general discomfort and all those sorts of lovely things. What I'm doing here today is starting a video series that I'm going to put together, which is based around archery equipment, kinetic energy and momentum. I'm planning on introducing the physics behind kinetic energy and momentum in a way that allows bow hunters to apply them to their equipment. So why I feel like it's necessary to do this is because in the archery world in general, I see that there are people that get into the sport and rely heavily on what other people tell them, and also what you know, your pro shops and things like that have to say on the matter, and as to what equipment you should be choosing. And I'm not officially saying that they're incorrect, but I'm just saying that the physics that's used to explain how our equipment works is actually pretty easy to understand, and that we can be more independent with how we apply this science to our equipment and our gear. We don't necessarily need to rely on what other people tell us. There's really simple ways for us to work out what our equipment's capable of doing on our own. So I'm putting out some videos out there that are aimed at helping hunters better understand the forces that are at play with their equipment, being potential energy, momentum, and kinetic energy, and which parts of the archery system those sciences apply to, so that we can get our head around what we should be focusing on when we're picking things like our arrows, our bows, our broadheads, and our practice targets. Even those things. And there are some simple tools that I believe every bow hunter should have in their kit that they potentially don't. I think a lot of hunters rely on what other people tell them. And there's like, for instance, I live out in the country and I don't have access to ready access to the bow stores that are around here, or the archery stores. So that means that I need to do a lot of my tinkering myself, and have to have a deeper understanding by default, because I can't rely on anybody else to do it. So for someone like me, when I do these videos, you're going to see me using equipment, and the reason I'm putting this equipment in the video is because the equipment's cheap and it's easy to use, and I just think that everybody should have them. To rely on somebody else's opinion when it comes to what another hunter should be using with their gear, I just don't see the point in that, when you could go and buy equipment that will, for not much money comparative to archery products, like a bow scale, for instance. You can pick one of those up for like 30 bucks, and you compare that to the price of arrows and your bow, your camo and all that sort of stuff. It's negligible. And what it allows you to do is have independence in selecting your gear. So what I'm going to start by doing is going over to some graphs that I've prepared already, to start off by explaining Newton's law of momentum, and seeing how we're going to apply that to our archery setups. So I've got here a bit of information on momentum. It's the Newtonian force of momentum. So we can see up here in the top left hand corner, we've got some dates. We've got 530 AD and 1687, and this represents the period of time that you know, well, Google will tell us that the idea of momentum has been around for. That's if you're only including up to Isaac Newton himself. So obviously it's still around. We haven't disproved Isaac Newton's his work on momentum. We still have Newtonian laws of physics. So
what this is simply showing is that it's an idea that's been built on over quite a long period of time. And that first name we have is John Philoponus. John Philoponus, from what I've learnt from him, is that he was this Greek fella, and he noticed that there was a relationship between two objects, one object having velocity, an object having velocity and mass, and its potential to do work. And he called it something else. He didn't call it momentum. You'll have to look into that yourself, but essentially what you're seeing is that it's a very old concept, and it's a thing that people started to notice a very long time ago. And Isaac Newton was, I suppose he's the name that everybody remembers when we talk about momentum and the Newtonian law of momentum. So that's just a sort of a brief history on how long the idea of momentum has been around for, hundreds of years, and it's been built on as we've gotten cleverer as a species. So over here we've got a graph representation of momentum, and we also have the equation. So momentum is expressed as P equals m times v. So mass times velocity equals P, which is momentum, right? And up here I've just got some labels next to it. So we've got P equals momentum, V equals velocity, and M equals mass in slugs, right? So why do we measure momentum in slugs for archery? Well, I suppose what that calls for is a little bit of research into what the term slugs actually means. So slugs is an imperial weight measurement. So we've got like grams, kilograms in metric, and in imperial, for the terms of archery, we have pounds, we have slugs, and we also have grains. So grains gets converted into slugs, as far as I understand it. There could be other reasons for it, but grains gets converted into slugs because it's a friendlier value to use. If you were just to use grains for this, you'd end up with results with lots of decimal points, and it just seems that a unit of a grain is much smaller than a slug. So, and also later on, as we run all of these things through calculators and stuff like that, it's going to serve us well to translate our arrow mass in grains into slugs for those two. So we'll get on to the graph here. We have a graph here that it's like a representational graph of the equation. We'll just say momentum equals mass times velocity, right? So over here on the vertical axis here we have P, and this is how much momentum our graph is going to spit out. So this is where we get our result from over here. On the bottom we have velocity, how fast our object's moving, and here, this part here was a little bit confusing for me, because as an archer who's looked at graphs and stuff like that for a number of other reasons, your initial thought would be that because the graph goes like this, it's just like, well, the more mass I get, yada yada yada. Well, it's not. So in this equation, this linear representation of the equation being labelled as mass actually has mass being constant. So if we start with a 10 kilo object here for this graph's purposes, it's the same weight up here. 10 kilos is the same no matter where we are on our graph, okay? If we have this is the reason why. If we have a look at our definition, our equation's definition here, it says that momentum is a linear function of velocity. If we double velocity, we get double the momentum, okay? So we'll do this, we'll do a little thought experiment here to help describe how it works. If our mass is 2, we'll just say it has a 2 value for easy maths, right? So that means our mass is 2 everywhere along that line, right? And if we have our velocity down here and we just take a value, we'll say 2. So if we have 2 times 2, we get 4 for our momentum for our object of flight, right? 2. Okay, if we double our velocity and go 4 times 2, the constant weight of our mass, we get 8. So if we double our velocity, that gave us 2, to 4, we get 8. So if we double the velocity of an object that has constant mass, so we keep our mass the same, we get double the momentum. Double the velocity equals double the momentum, right? The second point is that momentum is not conserved in archery's elastic collisions and open systems. So if you have a look online and you want to research momentum and learn about the sorts of things that impact on it and like some statements regarding to the nature of momentum, you're going to see it mentioned quite a lot that momentum is always conserved, right? That's only true in a closed system, okay? In an open system, momentum gets converted into other things, right? And we're going to learn about that a little bit in a second, but archery, the collisions that we have to deal with in archery are always inelastic in nature as opposed to elastic, okay? So we've talked about an open system versus a closed system. An open system is, well, we haven't actually, sorry, no. An open system is one where an object in a collision in any experiment involving momentum herein, we'll say that an open system is one where there are outside forces able to exist on it, right? And a closed system is one where where outside forces are not able to influence it at all. So to do this, we'll just do a little thought experiment to help me explain it a little bit better, right? Let's pretend these two items here are billiard balls, right? Now billiard balls are hard, right? They're two hard objects, and we'll just pretend that this one here is stationary, it's not going to move. If this one here, this billiard ball, is moving towards this one, right, and it's stationary, it's not going to move. Imagine it's been drilled through the center into the table and it's not going anywhere, right? As this billiard ball hits it, it's just going to bounce off it because of the hard natures at play here. This one's not going to move, and this one is just going to bounce straight off it in what they call an elastic collision, okay? If this billiard ball was made out of something else, like say foam, right, then this billiard ball, which is hard, is going to bump into it, and this one is going to compress, absorbing some forces that we're not going to talk about yet, but it's going to absorb some forces, and it's going to affect the collision in a different way. If it's hard, one hard object bouncing into another one is just going to cause an elastic collision, where this one's just going to ricochet off it, okay? But if this one is a different sort of material, like a softer material, like think like a car crash. If a car bounces into another car, they're designed to compress and warp and change and get damaged and all sorts of things. So they're inelastic collisions, and sometimes you'll end up with two cars getting stuck together nastily in a car crash and all sorts of things. But imagine if these are now two steel bins, like those big industrial bins that you see rolling around the place, and they're on wheels and shit. If one of them bounces into another one, right, and there's the material that they're made out of is strong enough so that it doesn't warp and bend, it's an elastic collision. But if they do warp and bend and break and change and things, it becomes an inelastic collision. If we apply that to archery, archery is full of inelastic collisions, right? Only if you shoot your arrow at a bowling ball do you get an elastic collision. And even then, I would say your arrow is probably going to break and shatter, and it's going to turn into an inelastic collision, okay? So the open system of archery as opposed to a closed system. A closed system relates to, say, let's say we were shooting, well, let's say we're rolling our billiard ball into another billiard ball that moves in space, where it's in a vacuum, and there's no perceivable gravity at play on anything. There's no resistance. There's no drag. There's none of these sorts of things. We're going to get very different results, and it's dependent on the system. So if it's in space, we go boop, and then the two objects are going to move off together in space, right? If we bring that down to Earth, it's not the same anymore. We have gravitational influences on both the target and the other object. Sorry, the billiard ball, whatever the fuck it is. Sorry, excuse my French there. It doesn't matter, but it's got external forces at play on it. It's got gravity. It's got drag. So this object, if it's on Earth, it has drag. It has all sorts of. We've got heat loss as well. That's going to come into play, specifically if it's not a elastic collision. We've got lots of things acting on our collision. and therefore that is going to make it an open system, right? So we'll move on. Now that we have an idea of what an elastic collision is versus an inelastic collision, and what an open system is versus a closed system, we can tell that archery is an inelastic collision, pretty much always, you know, unless I said before, like you're shooting a bowling ball. And it's always going to be in an open system. Bow hunting is outside. It's always going to be an open system. So we'll move on, right? Momentum is a vector quantity, so you can have positive and negative momentum, i.e. an arrow having positive momentum and a target moving towards it having negative momentum, right? So that simply means that, let's say over here we have our billiard ball moving across the table this way at a certain pace, and this one here, this billiard ball is the one that we're measuring the momentum of, right, in a linear direction, is moving over towards it at an even faster pace than this one, right? So this one's moving slowly, this one's moving quickly. This one has a positive momentum in the representation of what we're measuring here, and this one has a negative value of momentum, right? So it has a negative value of momentum and therefore a negative consequence that's going to play out as we perform our measurements of momentum in this collision, right? So you can, that's all this is saying, is it's a vector, so you can have positive momentum or you can have negative momentum, right? Momentum is a directional force, and the target moves with the line of the arrow, right? So let's say this is a foam target and we hit it, and you're watching a target get cleaned up by an arrow out in the field. Maybe you're shooting archery with some friends and you see old matey's arrow coming towards the target and he hits it, and this target moves slightly, right? Well, that slight movement this way, sometimes if it's not a very big target, you'll see it go like that, okay? And that is momentum being transferred from the arrow into the target, okay? So it's kind of like our billiard ball, but it doesn't just bounce and move away because of the nature of the material. It's an inelastic collision, and so you'll see it move ever so slightly as it absorbs the momentum from the arrow. It will move away from the collision, right? And so that's what we're talking about here when we say that momentum is a directional force, right? When you hit it, it doesn't move that way, okay? Unless, let's talk about it in a hunting situation. This is a pig or a deer or something, and it's moving towards the line of where our arrow is coming from. It's carrying with it negative momentum, okay? The arrow has positive momentum, the animal moving towards the arrow has negative momentum, okay? And these will definitely impact the results that we get after the collision. So let's move on. What is an open system versus a closed system? I feel like we already covered that. And what causes momentum loss? So in a closed system, like we talked about before, like say we're out in outer space and we're in a vacuum and there's like very little perceivable gravity that are at play with these two billiard balls floating around in space hitting each other. That's a closed system, okay? And in that closed system, those descriptors that you'll get on the internet talking about momentum always being conserved, they're strongly correlated with it being a closed system, right? In a closed system, momentum is always conserved. And that is that one object hitting another one in a closed system, they're both going to move away. If one was stationary, they're both going to move away at a rate that was comparable to the amount of momentum that this first object had. It's transferred into both objects in a closed system, like outer space in a vacuum, and they're both going to move away together, right? So momentum is conserved there. We can see that it's conserved, it's not lost anywhere. But in an open system, where there's external forces at play, momentum will be deteriorating in this object, okay, and it's also going to deteriorate to a level of both objects. So let's say that they're down here on Earth, okay, and we've got gravity, we've got drag, we've got all sorts of other forces at play on the collision. There is going to be some loss, okay, and that's what this question is relating to. A lot of the arguments that you hear versus between kinetic energy and momentum, you know, some people I've heard some people talk about this from the perspective that, oh well, you can lose kinetic energy, you can't lose momentum. It's just not true, right? And I'm going to demonstrate this with a little bit of help from AI, since that's what everyone likes to use at the moment to help them describe certain things that they want to say. If I type into here that momentum is conserved in a bow hunting collision, it says, yes, momentum is always conserved in a bow hunting collision or any collision, provided you define the system correctly to include all interacting objects and include external forces, right? But if I go over here and say, is momentum conserved in an arrow during a bow hunting collision? It says, in an arrow target collision during bow hunting, the momentum of a single arrow is not conserved because there is external forces acting on it, the resistance of the target material. However, the total momentum of the larger system, the arrow and the target combined, is conserved during the brief moment of impact, provided external forces like friction and gravity are negligible during that short period of time, all right? So it's having a hard time explaining the external forces part of what we were talking about before. And ultimately, all of this gets really, really tricky and complicated. And you need lots of equipment to account for a lot of that energy loss. But what I'm preparing to show everyone is that it's evident in tests. So when we carry out our own tests at home, we can sort of get a feel for what playing around with our arrows is going to achieve downrange by applying some of the science that goes into calculating momentum into our gear and just simply seeing what it does out in the field. Okay, now that we've got that tricky part out of the way, let's have a look at how we can start implementing it into our archery gear simply, right? So I'm going to start with a clean page here. I'm going to label it momentum, because what we're trying to do is, we're going to try and boost the performance of some arrows here using momentum. By increasing momentum, we're going to see if we can boost the performance of our arrows, right? This is a common practice in bow hunters everywhere in Australia, I've noticed, but I'm not sure if anyone actually does this at home when they're doing it. I'm fairly certain that there's just a general belief that if you simply add mass, you're going to get better performance out of your arrows, right? And that's usually the type of understanding that we rest on in archery or bow hunting here in Australia. What I'm going to do now is to start jotting down some values. So we're going to do an experiment on 2 different arrows. So I'll start by writing down, so I've got my arrows here and I've just put a stripe on one of them, and the striped one is going to be the modified one, and this is going to be our unmodified arrow. So it's going to be the same weight as they always were, and this is going to be the test arrow, or the arrow that I'm sort of pretending here that we've bought extra gear for it, or we've bought another arrow and we've somehow made it heavier or given it more mass. Okay, so I already know the 2 weights and how much I've actually increased it, and my original arrow weight, sorry, excuse all the noises here, it's a bit of a windy day. I obviously won't be doing the testing today due to the wind. That'll be on another video, but so just for now we're going to start doing some of the preparation maths for the testing, and this is all stuff that you can do at home. It is actually really easy, and it doesn't cost you a lot. So the first thing we're going to have a look at is a bow scale. So we need to get the measurement of our bow's poundage for these sorts of experiments, so that we can get an accurate read on velocity. So we need to know the velocity output of our arrows, and to do that we need to know what sort of poundage and what speeds our bow's setting up. Our bow's spitting out. So these things, you can pick them up for like $30, man. You can pick them up from pretty much any archery store in Australia. They should have one. I know Abbey Archery sell them. Apex Hunting probably sell them. I'm guessing Venture Hunting's probably going to sell them as well. They've got a pretty great range up there, up the coast. So these things are very affordable, and yeah, I just think, you know, anyone with a bow is going to need one. They're cheap. So what we're going to do is we're going to get a reading on my hunting bow and see how much poundage it's actually putting out. Okay, so first thing we want to do is turn it on, and we want to hit the unit button to change us from kilograms over into pounds, and we set it up. Well, this is how I set mine up. I just tie a rope to a roof rafter, a nice rope, make sure they're really good knots, and we give it we do a tear weight to zero it. And we hook this over the hook. So we got 68 pounds. I like to do it a couple of times just to make sure that we've got a good reading. 68 it was. $69.8. We'll do it one more time. $69.7. So I'd say that's pretty close to 70 pounds. So we go over here to our piece of paper and we just write down £70 for our bow weight. Now what we're going to do is write down 2 columns. So these are going to be 2 columns that are going to represent our 2 arrows. So our current weight, which I know to be 400 grains, right? And our modified weight. And for this experiment, what we're going to do is we're going to add 150 grains to our arrow, right? So we're going to add 150, making it 550. Oh, I've already stuffed it up, mate. 550 grains. Okay, so we're going to have 2 arrows, one 400 grain and one 550 grain. And to do that, what I'm actually doing to get the 2 arrow weights is I've got my standard setup here. Again, this is a very cheap item to get a hold of. I recommend buying it from a archery store, because you know it's going to have the sensitivities that we like to use for archery gear. So it has the grain weight function. So just make sure I've selected that, and then we're going to put our control arrow, as I'm calling it, for the test, and its weight is 399.2 grains, 399.6 grains. Okay, so that's pretty close to 400 grains. You know, you could be more exact if you wanted to, but I don't really think it matters here. It's just a 400 grain arrow. Okay, and I already know what the next one's going to weigh. For this test, what I've actually done to get a 500 grain arrow is I've used. You guys can do this yourself at home, but what I'm going to show you is that you ultimately don't really need to do this. You can rely on the calculators that I'm going to show you to sort of, you know, do this better. Like, I'm just doing it for the test to show how it's going to perform. You can play around with these yourself, but essentially what I'm going to be doing is I'm going to be filling one of these arrows up to get the weight. And when you fill arrows up with things, there are some considerations to make. The material inside the arrow can't move, because if it moves, it's going to negatively impact the performance of the arrow. So to make it so that it doesn't move, whatever you jam in there has to be tight. And I mean, like, it's got to be tied up against the inside of the back of the nock, right? So our arrow nock here pushes into the back of the arrow, and whatever substance you put in there, I mean, like, I've heard of guys using things like salt. I know John Dudley has gone over and hunted using a 7 or 850 grain arrow over in Africa to shoot a giraffe, I think it was, and he said that he filled his arrow up with salt. Unless you can guarantee that salt's not going to move inside it, I would say that it's not. I don't recommend doing that, because I've tried to put objects in these sorts of things before, and if they do come loose, they can cause your nock to fly out the back of the arrow. But for this test, what I've chosen to use is fly screen spline. Now this stuff fits perfectly. It's just the right diameter to fit snug inside my arrow, and I can push it all the way up the arrow until it's at the top. And you can see I'm actually using 2 pieces. And that was because I cut this a little bit too short, and there was no pressure against the back of the nock. So I feed it all the way down the arrow shaft, and then I push this last little bit in there, and that's what gives me the resistance against my nock as I push it in there. So that when I fire my arrow, the guts of it aren't going to move up and down inside the shaft, which I believe would create a negative effect on the results that we're going to be trying to record. But for this specific test, I know that this doesn't move inside it. So I'm going to go ahead and stick it in there. So just bear with me while I do that. Right. And of course, we're going to have to nock tune this again to make sure that we get our fletchers are in the right position for our rests. So I just push that in there. Right, get our last little bit and put it in there. It's tight, and then I push that in there like that. Okay, and we're snug. Okay, so now we can weigh our second arrow, and it should say 550. Bingo, 550 grains, 0.4. Okay, so we've got our heavy arrow marked with white for the test that we'll do in the next video, and our lighter arrow, which is 400 grains. So we've got a 400 grain arrow and a 550 grain arrow. The next thing we're going to do is introduce the speed calculator. So we'll go over here to my tablet. So on my tablet I've got bookmarks. Alright, we've got an arrow speed calculator. I'm going to include links to all this stuff at the bottom of the video so that you guys have access to all of them. And I picked the most accurate ones that I could find that are going to give us the simplest results. Because sometimes they exclude things and include things that don't need to be there and exclude things that do. So for this one, this is a really good arrow speed calculator because it includes this bit here, weight added to the string. So you definitely need to consider that. I've talked to a couple of archery stores in the country already, to guys that have done this sort of thing. In particular, a guy who did a study on how much impact those little weights that are on your bow affect the speed ratings. So these little guys here, and essentially there's variations between all of them. Those little speed button things, their weights can vary from 6 grains all the way through to 20 or 30 grains, right? So, so I'll just get that still. And I talked to the guy, this was in Archery Supplies South Australia, and he said that the effect on arrow speed is like up to three feet per second. So you can account for that as well in your results if you want to, but he said the thing that is a consistent way to use is just make sure you include the peep sight. So I've gone ahead and put some of this data in that we've already got. The IBO speed is something that you might have to look up if you've forgotten it, but for my bow, it's 345 feet per second, and that arrow speed is based off a 350 grain arrow, I believe. So it's an arrow weight that we would never even use in hunting, or you shouldn't be using anyway. It is too light, because if we use these calculators, we can see that we won't get enough kinetic energy or momentum to be able to do what we need to do. So the IBO speed is just like what I believe for these calculators is a base speed for them to work off. And you just need to know the base speed for your bow, the bow that you're using to do your testing on. So as you can see, mine's quite a fast bow. It's quite a high IBO speed. As a matter of fact, I know I bought my bow because of that. I wanted to have the highest possible velocity output I could get from my bow equipment. And that's advantageous for a number of reasons. It gives us a lot of options because bows are adjustable. You can increase the amount of bow speed you're going to get out of it by changing your limb pockets. They increase the poundage that the bow can put out, and therefore they impact the amount of speed, the amount of velocity it's able to give to our arrows. So so I put that in there as 345. The draw weight, as we just did on our bow scale, we worked out that it was 70 pounds of draw weight. So that's recorded here on the top left-hand side of the page. And our draw length, so my draw length is not 30 inches. It's I think it's 27.5 actually. Yep, 27.5. Okay. So for us to get our arrow speeds and add them to our paperwork, we're going to have to play around with the two weights that we've got now. So one weight is 400 grains. So we just want to, and you can do this yourself with your arrows without actually having to go out there and buy a heavier arrow to do a test with. You can just use these speed calculators that I'm going to give you to crunch the numbers so that you can get an idea for the sort of performance that you're looking to get out of, changes to your gear. So if you're looking at shooting a slightly heavier broadhead, how much extra momentum and kinetic energy are you going to get out of it, right? That's where the usefulness of this comes into it. Sometimes it won't be worth the amount of money that you spend on your equipment. Let me just tell you that much. Come on. 400 grains. Perfect. Okay. So we have estimated arrow speed of 297 feet per second. Okay, so we're just going to go and record that as velocity. Equals 297 feet per second. Cool. All right, now let's also do another calculation for the heavier arrow. And all we need to do here is increase the arrow weight from 400 grains, let me do it, to 550. So if we just push that all the way up to the proposed 550 grains, we get 247 feet per second. We go over here, 247 feet per second. All right, nice. So now that we have those two values, we're going to convert our grains into slugs using Google, right? So we'll just go, I don't know, back, or yeah, there we go. Convert 400 grains to slugs. Okay, 0.001 will go 8. We'll just round that up. So 0.0018 for this one. And that would be our mass. So M equals 0.001, just make sure, 8. Okay, in slugs. Okay, cool. Now we'll ask the same question for the heavier arrows. So if I just go here, 550. Okay, we have 0.002 and 444, so it would be just 4. So we round it down, so 0.0024 for the heavier one. Mass equals 0.0024 slugs. Cool. So now that we have all of these values, we have our initial grain weights, which simply at this point serve, because we've already converted them into slugs. Our grain weights just to serve as it's like a visual reference to know, you know, we're talking about the lighter arrow here and the heavier arrow there, because we've converted it from grains into slugs. Right, but we have our M value now, and we also have our V value. So if we go back to our momentum equation, all we needed to work out our momentum was the mass times the velocity, right? So what we're going to do is, I've already saved a couple of calculators online so that we don't have to do crazy maths. Because that's not fun. I don't like doing that. But if I can find a good calculator, that makes life a lot easier for me. So I've just bookmarked them here. All right, now this is a great calculator. It's an honest calculator. It doesn't have any sort of archery methodologies attached to it at all. So it's it's a good third party. And it's a T2E. So if you just Google or turn to engineering.com, right? That has a nice ring to it. Anything to do with engineers, I'm going to be supportive of because they're very smart people. So we have, we're going to solve for P, and the main result in units, we don't want kilograms per meter per second, right? Because that's metric. Everything we do in the archery realm is in imperial, and we have there as an option, it gives us to select a result giving us slug feet per second, which is what we want. Because everybody in the archery world is going to know what you're talking about if you give momentum results in slug feet per second. So we're just going to plug in our values now from our paperwork into the calculator, and we have our mass. Okay, so it's asked us to put in our mass in kilograms, so we need to change that to slug, right? Change the mass to slug, and we're also going to change our velocity from meters per second into feet per second. So now we have a momentum calculator that is purpose built for our archery needs. So we have a mass of 0.0018, right? So 0.0018, and a velocity of 297 feet per second. So 297 feet per second, and that will give us our results. So our result for the light arrow is 0.5346. It's not a very long number, so we'll give it all of the decimals, and we'll write them over here. So we can now give our result for P, or momentum, the momentum of our light arrow is 0.5346. Cool. Okay, we'll go back here and we'll do the same thing for our heavy arrow now. So our heavy arrow, we're going to change the mass and we're going to give it 0.0024. So 0.0024, and the velocity, our velocity was 247 feet per second. So 247 feet per second. All right, so our momentum is 0.5928. So P, our momentum is 0.5928. Cool. All right. So well, now we've done our homework, and we know what the perceived increase is going to be for our arrows. And as we can see here, we've been given two different values. So straight off the bat, we can definitely see that the lighter arrow, the 400 grain arrow, has less momentum than the heavier arrow. So the heavy, and that supports the maths. Like we said before, we have, well, I suppose in essence it kind of doesn't, but the maths has changed because we don't have a constant mass. Our mass has changed. So remember in that graph I showed you, it had a linear representation of the equation with mass as a constant. But we have, this is why we use a calculator, right? Because our mass isn't constant here. We're actually measuring two different masses and two different velocities. But like the equation said, if we double our velocity of a constant mass, we double our momentum, okay? But what we're seeing here in archery land is a situation where if we increase our velocity or decrease our velocity, right, we're going to actually affect our momentum due to a change in mass. So we're changing our mass as well. So we're changing velocities and we're also changing mass just by changing mass. So what we're seeing is that when we increase our mass, we're actually slowing down our arrows. Out of the same bow, our velocity is decreasing. So where it was 297 feet per second, if we add that much mass to it, it slows it down to 247 feet per second. So with the equation that we had where, the increase was based on doubling the velocity of a constant mass, we're seeing our velocity change as well. So we run it through a calculator, and what we have is a slight increase in momentum, and your version of slight is going to depend on the effects downrange. What we're going to see when we shoot these two arrows is how much benefit we're actually getting by just increasing momentum by that much, okay? So our momentum that we had was 0.5346, and what we ended up with was 0.5928. So there's no ifs or buts about it. The heavier arrow has a higher momentum value, but it also has a lower velocity value, okay? But if we're just wanting to increase momentum, I'd say we've successfully done that. We've successfully increased momentum by increasing the weight by 150 grains. And now what we need to do is see how the two arrows are going to perform downrange. So what I'm going to do is I'm actually going to stop the video here. I'm going to include all of the calculators that I've used in the video notes, along with some of the equipment that I've used, being the bow scale and the arrow scale. Like I've said, you can hunt those items down at your favourite archery store. Hopefully they've got them for you. But in terms of the calculators I've used, I'm gonna add them to the footnotes in the comments. Thank you for sitting with me through all of that. The video went for a little bit longer than I thought it might. Hopefully it wasn't too much for you guys to get your head around. The benefits of using these these calculators with our archery gear are going to become more apparent when I actually do the practical. But if you can get your head around doing that that paperwork, writing down your values, using your bow scales, it actually doesn't take that much time. It's quite easy. You just need to figure out the speed that your arrows are getting launched out of your bow, and the only piece of equipment that you need to do that is get a bow scale. So if you buy your bow scale, you can work that out. And yeah, the process of playing around with the theory behind what might happen if I increase my arrow weight or my bow speed by this amount, yeah, you should be able to get your results quite easily. And that was the purpose of this video, is to sort of introduce everybody to momentum and look at how we might practically apply that to our archery gear. So in the next video, what we're going to be going through is the practical. So I'm going to talk to you about what materials I've chosen to use for my target, the distance that I'll be setting the target up at, but it's going to be quite fun. It'll just be a video showing me essentially shooting the two arrows and seeing how they perform. So based off our momentum calculations, I suppose things that we're going to be looking for is an increase in performance from the arrow with the greater momentum. And that will simply show us that by using a momentum calculator, we'll be able to verify just how much of a difference that's going to make. And hopefully for any of you guys out there watching the videos, if you're thinking of changing your setups by 100, 150 grains, or making them lighter or making your bows faster, you'll be able to use this calculation to work out whether or not it's actually going to make any difference for you versus the amount of money you're going to spend on it. Anyway, hope you guys have enjoyed the video, and stay tuned for the next one.